Hey guys, today we are looking at a concept called variation. It studies the relationship between two or more variables. So what's a variable? Variable is a quantity that keeps changing or varying. See, basically variation is about how the movement of one variable affects the movement of other variables. We have already covered concepts like ratio proportion in another video whose link is given in the description below for your reference. You may go through these videos along with what I am going to discuss here in variation, because these three concepts are to be studied together. Okay, let's focus on variation again. Take two variables, say x and y. Basically, there are two kinds of variations. One is called direct variation and the other is inverse variation. Let's discuss first this idea, direct variation. As I said, take two variables, x and y, and if these two variables vary in such a way that the ratio always remains the same, which means whatever be the values you take for x and y, finally after finding this, x by y will lead to the same number. And that same number or a constant value, if you get, we call it k, then we say that x is directly proportional to y, or x varies directly as y. Mathematically, you write it like this. So this is the definition of x being directly proportional to y or x varying directly as y. These two variables change in such a way that their ratio always remains the same. Or you can write, this implies x by y equal to k, which implies, you can put it this way, x is equal to ky, where k is called the constant of proportionality. I will take you to a real life situation to get a better understanding of whatever concept I've gone through just now. Supposing something you're buying, say let it be sugar, which costs say rupees 50. This is the price of 1 kilo sugar. Now, supposing you are buying 1 kilo, how much money do you pay? 50 rupees. Or rather, this is the expenditure. Expenditure, quantity. Now, supposing you buy 2 kilo sugar, obviously you pay 100 rupees. You're buying 1.5 kilo, you pay 75 rupees. If you're paying 10 kilo, you end up paying 500 rupees. So what do you observe here? The more the quantity you are buying, the more the money, or rather the expenditure you are incurring. So these are two variables. You can call this x and this y. If you take x by y, this ratio, in the first case you get 50 by 1, in the second case you get 100 by 2. Like that it goes. Look at that. Whatever be the different values x and y are assuming, finally, while taking the ratio, they all end up being the same, and that same number in this case is what? 50. And 50 is the constant I refer to here. So this is a simple example to illustrate the concept of direct variation. Now there is one more thing you can observe here. If x is directly proportional to y, or taking one set of values, this will be x1 by 1. Taking another set of values, this will be x2, y2. Like that it goes on. So x directly proportional to y implies this, or x directly proportional to y, x by y as constant. Either of these two we use in solving problems depending on how the problem is framed. Something more you can observe here. When you have x being directly proportional to y, the more of something, the more of the other. Rather, the increase in one variable will trigger the increase of the other, or a decrease in one of them will lead to the decrease of the other variable. Rather, these two variables will move in the same direction. There is something I would like to let you know in this context. Just because you have two variables moving in the same direction, they don't have to be in direct proportion. But you have two variables which are directly proportional to each other, then certainly they will move in the same direction. Rather, what I meant to say is, moving in the same direction is only a necessary condition. It's not a sufficient condition. That's why you don't see the converse or the reverse being true. Keep in mind this point. The second kind of variation is inverse variation. Take two variables. X and y. We say x is inversely proportional to y, or where x varies inversely as y. This is the mathematical notation for that. If x and y move in such a way that their product always remains a constant, which we have represented by k here. And k is called the constant of proportionality. So it goes like this. X is inversely proportional to y implies xy equal to k. I'll show you some example to illustrate this point. Supposing you are going from your home to college on a motorbike, say at a speed of 50 km per hour. So what will be the time taken by you to reach the college? 1 hour. Now the distance from your home to college is a constant. Now, as you can see, the faster you move, earlier you reach the college, and the slower you move, you take more time to reach the college. So speed and time, we say, are inversely related to each other. For example, let's denote speed by x and time by, say, y. See, on the first day, you moved at 50 km, you rode your bike at 50 km per hour, yeah, you take 1 hour. Supposing on the next day, you reduce the speed to, say, 25 km. How long will it take? 2 hours. Similarly, so these are the different values of speed. These are the different values for time. Now look at the product of these two. 50 into 1, 25 into 2, 100 into 1 by 2, 75 into 2 by 3. They are all equal. And that equal number in this particular case turns out to be what? 50. And that's what is denoted by k here. So in every inverse proportionality, there is a constant number called the constant of proportionality, which in this particular case happens to be 50. And we say x is inversely proportional to y. So You can interpret this in another way. Supposing this is x1 and this is y1, and if you take the product, this is what you get. You can name this x2 and this one y2. You get the same product on multiplication. Rather, these two are equal. So x inversely proportional to y, you may write it as xy equal to k, or another way to write it is x1 y1. I mean, taking two sets of values and finding out their product, they will turn out to be equal. If you take a third set, again that will also equal this one. Now, we use either this or this in solving problems on inverse variation. Now, there is something else I can derive from this. Look at this. X directly proportional to y. We are using the basic definition xy equal to k, which implies taking y to the other side, you have this form. Now, if y is a variable, what will be this? 1 by y will be another variable, and x is the first variable we have chosen. Now, this implies what? This is similar to the direct proportion we have already covered, which means x is directly proportional to 1 by y. Rather, you started here and it took us to this step. So what is the observation you are making? If x is inversely proportional to y, then you can say x is directly proportional to the reciprocal of this variable. This is also a useful idea in problems on variation. Now, there is one more additional concept to be covered here, which is called a joint variation. In joint variation, there are more than two variables. It could be 3 or 4. Let's look at 3 variables, x, y, z. Now, I'll define joint variation first before showing an example to illustrate this point. This is the definition. If x is directly proportional to y, when z is constant and again x is directly proportional to z when y is constant, then x is directly proportional to the product of these two variables. This is the definition of joint variation. Now let me take you through a simple example to illustrate this idea of joint variation. You take a cylinder. I hope all of you know what a cylinder is. Cylinder has a volume, it has a radius, and then it has height. Now, first you look at all cylinders with the same height but different radii, and you will see that V is directly proportional to R square. Here H is kept constant. Now you look at another set of cylinders where you have the same radius and the heights differing. In that case, you will see you will see V being directly proportional to H. Here R is constant. Okay, so what is it that I have done? In the first case, I have taken all cylinders with their height being the same. And if you look at if you measure the volume and then if you measure the radius, you will see that V is directly proportional to R square. What does that mean? That means if you take the ratio of V by R square, which is how we have defined direct variation, that will always remain same. In the same way, in the second case, you are looking at all cylinders with the same radius but different heights. In that case, if you take these two measurements, obviously these two will keep differing with this being the same. If you check out the ratio of V by H, that will always remain the same. Rather, V will be directly proportional to H. Now look at this. You can compare this to the definition. So combining these two, this is the result. What do you have? V will be directly proportional to product of these two variables. And that implies what? V equal to, this is the basic definition of direct variation. There is a constant which is called a constant of proportionality in R square H. So can you guess what this constant of proportionality here? As you know, it turns out to be pi. Rather, this is the volume of cylinder, pi r square h. See, I haven't derived the volume of a cylinder. Here I've taken up this example to illustrate this point. The derivation of volume of a cylinder is done in calculus, which is not within the purview of any competitive exam. So let's forget it. But this has helped you to get an idea of the joint variation, which is also useful in many problems. If there is any point you haven't still correctly understood in my discussion on these two different concepts called inverse variation and direct variation, feel free to raise it in your comments. I will address it there. See you guys in my next video, where I will help you with some simple problems to illustrate these two concepts, which will give you a better understanding of these two concepts. Bye for now.